Now, if you have seen Game of Thrones, you probably know Jon Snow's journey back to the Winterfell. He's traveling from Dragonstone to Winterfell in GOT environment. So here the states are Dragonstone, White Harbor, Winterfell, and the terminal states are Dead and Alive. Actions for each state is shown in the video. Think of each of the locations as states, and the score of Jon Snow's safety can be thought of as state value. Please note that the action is always with respect to the state, and the reward is associated with action and not the state. The exception to this rule is terminal states, which can be initialized with some reward and it doesn't change. So from Dragonstone, you can be traveling on a dragon or sailing through the narrow creek or going via forest and so on and on and on. Our goal is to find out three things. What is the best action at any point? Now that's policy. How rewarding is it to be at any state? It's like sensing how dangerous is White Harbor. That's called state value. The third thing is, these rewards can also be calculated for an action and are called action values, which tell me the expected reward for an action. Let's have a look at the code here. V is nothing but dictionary of initial state values. Note that initialization in general doesn't matter, but for terminal state it does matter because it doesn't change. R is the dictionary of reward for each action that sprouts from a state. So R of from Dragonstone C gives me the immediate reward for traveling via sea. Q is nothing but initial action values. They are currently initialized with immediate reward. P is state action state transition 3D matrix. Why is it 3D? Because we have SAS dash or state action next state pair for transition probability. It tells me that from White Harbor, if I went via land, then what's the probability of me going to the Winterfell instead of dying? Now let's look at the core logic. Okay, the first outer loop is for the iteration. The second inner loop is for the update of the state values for each location. So in order to do that, it first updates the Q value for each action sprouting from that state. This is done by adding immediate reward with discounted probabilistic sum of state values it can land up in. Now the value is updated based on the max Q values. The policy is also updated simultaneously. That's that. There's nothing more fancy. It's just 9 lines of code. Also note that you can swap the state value update and the action value update step. It won't make any difference. These are two different ways of coding the same thing. Mathematically, they can be written as shown in the right side. If you notice, for the state value update, there is an intermediate calculation of action value. And similarly, for the action value update, there is an intermediate calculation of state values. When you study model-free settings in a future video, you will realize that updating action value is way too cooler and computationally efficient than updating state values. But for now, let this be a mystery. What you have just learned is your first comprehensive way of learning policy. Time for some party. Before I leave, I want to give you hints of the pitfall of this method. This maximization over action values of changing policy is a problem. It's like you decided to play poker and now you wish you had gone to football. And if you had decided to play to football, now the poker is bugging in your head. The convergence of steady state value in this case is very difficult. You'll be just wobbling around your decisions. In short, it takes longer time to learn this.